Section 15 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 11. Mercury. Ancient records make no mention of the discovery of Mercury, yet the existence of the planet was surely known even in the days of Nineveh, when a chief astronomer directly refers to the planet in a report which he made to King Assurbanipal of Assyria. The planet is occasionally mentioned in early and medieval astronomical literature. It is stated that Copernicus regretted that he had never been able to observe it properly in the high altitude of Frauenburg. That the planet should have been overlooked by the ancients is not strange when it is considered that it is never visible in the higher altitudes except occasionally near the horizon, just after sunset or before sunrise. In the clear sky over an eastern desert, the primeval astronomer doubtless saw this bright star in that part of the horizon where the setting sun was still shedding its beams. Its luster diminishes as the planet draws near the horizon at sunset, until finally it sets so soon after the sun that it is invisible. Years may elapse before a similar opportunity is afforded. If a similar phenomenon took place at sunrise, the primitive astronomer might have inferred that Venus and Mercury were identical, especially as a long series of observations would establish the fact that one of these bodies was never seen until the other had disappeared. Accordingly, some of the ancient astronomers assumed that there was but one morning and evening star. But as records accumulated, it was recognized that there were two bodies which might serve as morning and evening stars. A certain regularity in the recurrence of each planet was noted, and it was possible to make predictions of accuracy as to the time when either could be seen after sunset or before sunrise. While by the time of Plato it was known that Venus and Mercury performed their revolutions in approximately the same time, it was recognized that Mercury's period was different and more rapid than that of other planets. An older tradition, attributed to the Egyptians, stated that both planets revolved around the sun. Ptolemy states that they could be regarded as oscillating to and fro on each side of the sun. That the ancient astronomers might well have been confused by the appearance of Mercury as morning and evening star follows from a consideration of the planet's position and motion relatively to the sun and the earth. The consideration, moreover, applies to Venus as well. Quoting C. G. Dolmage's Astronomy of Today, "When furthest from us, Mercury is at the other side of the sun, and cannot then be seen owing to the blaze of light. As it continues its journey it passes to the left of the sun, and is then sufficiently away from the glare to be plainly seen. It next draws in again toward the sun, and is once more lost to view in the blaze at that time of its passing nearest to us. Then it gradually comes out to view on the right hand, separates from the sun up to a certain distance as before, and again recedes beyond the sun, and is for the time being once more lost to view." To these various positions technical names are given. When the inferior planet is on the far side of the sun from us, it is said to be in superior conjunction. When it has drawn as far as it can to the left hand, and is then as east as possible of the sun, it is said to be at its greatest eastern elongation. Again, when it is passing nearest to us, it is said to be in inferior conjunction. And finally, when it has drawn as far as it can to the right hand, it is spoken of as being at its greatest western elongation. The continual variation in the distance of the inferior planets, Venus and Mercury, from the Earth during their revolution around the sun will of course be productive of great alterations in apparent size, which no doubt also had its effect in bewildering the ancients. At superior conjunction, being then farthest away, Mercury ought to show the smallest disk, while at inferior conjunction, being the nearest, it should appear much larger. When at greatest elongation, whether eastern or western, it should naturally present an appearance midway in size between the two. From these considerations it would seem that the best time for studying the surface of Venus or Mercury is at inferior conjunction, or when the planet is nearest to the Earth. But that this is not the case will at once appear if it is considered that the Sun's light is then falling upon the side most distant, leaving the proximate side unilluminated. In superior conjunction, on the other hand, the light falls upon the side of the planet facing the Earth. But the disk is then so small, and the view besides is so dazzled by the proximity of the Sun, that observations are of little avail. In the elongations, however, the sunlight comes from the side, and so we see one half of the planet lit up, the right half at eastern elongation and the left half at western elongation. Piecing together the results given at these more favorable views, it is possible bit by bit to gather some small knowledge concerning the surface of Mercury or Venus. Consequently, it will be seen that the inferior planets show various phases comparable with the waxing and waning of the Moon in its monthly round. Superior conjunction is, in fact, similar to full moon, and inferior conjunction to new moon, while the eastern and western elongations may be compared respectively with the Moon's first and last quarters. When these phases were first seen by the early telescopic observers, the Copernican theory was felt to be immeasurably strengthened, for it had been pointed out that if this system were correct, the planets Venus and Mercury, were it possible to see them more distinctly, would of necessity present phases when viewed from the Earth. The apparent swing of an inferior planet from side to side of the Sun, at one time on the east side, then passing into and lost in the Sun's rays, to appear once more on the west side, is the explanation of what is meant when one speaks of an evening star or a morning star. Mercury of Venus is called an evening star when it is at its eastern elongation, that is to say, on the left hand of the Sun, for being then on the eastern side, it will set after the Sun sets, as both sink in their turn below the western horizon at the close of day. Similarly, when either planet is at its western elongation, that is to say, to the right hand of the Sun, it will precede him, and so will rise above the eastern horizon before the Sun, receiving therefore the designation of morning star. Mercury's motions were early studied. With the planet was associated the first of the remarkable astronomical predictions that now have become almost commonplace, so carefully are they worked out by astronomers. Kepler, from his studies of the motions of the planet, was the first to realize that if the orbit of Mercury, which, as has been seen, lies within that of the Earth, and thus nearer the Sun, were exactly circular, and in the plane of the ecliptic, a transit of Mercury across the Sun's disk would occur once in each synodical revolution, or period between two successive conjunctions of the planet with the Sun as seen from the Earth. The epoch of the transit could be calculated very easily. But Mercury's orbit is inclined 7 degrees to the ecliptic, and is very eccentric, for which reason his calculations were only approximately correct. It was in 1627 that Kepler predicted transits of both Mercury and Venus across the Sun, and assigned the date of November 7th for the former. Gassendi, to whom was entrusted the task of proving Kepler's prophecy, began his observation on the 5th of November, watching the image of the Sun formed by a lens on a white screen from light emitted through a hole in a dark room. But Kepler was not in error by as much as that. Only 5 hours after the time assigned did the transit actually begin. Thus was commenced a series of observations of the time when Mercury crosses the great central luminary of this system. These transits are by no means rare, for 13 of them were observed in the 19th century. They afford opportunity for observation which enables the movements of the planet to be calculated with accuracy. After the transits of 1661 and 1677, La Hire constructed new tables of Mercury and predicted a transit on May 5, 1707. The calculation was in error by nearly a day. After the transit of May, 1753, had been observed several hours later than La Hire's, and as much earlier than Halley's prediction, Lalande constructed new tables and predicted the transit of 1786, which actually took place 53 minutes later than the time announced by Lalande and about as much earlier than the time computed by Halley's tables. Lalande then corrected his tables and predicted the transits of 1789, 1799, and 1802 with a fair approach to accuracy. The tables compiled by Lindenau in 1813 still left much to be desired. The problem of Mercury's motion was in this condition when it was attacked by Leverrier, who was under no illusion in regard to its difficulty. Leverrier did not succeed in overcoming the difficulty until 1859. As a result of his work, supplemented by that of later investigators, astronomers are now in possession of at least fairly accurate information on the subject of the planet's orbital phenomena. It is known, for example, that Mercury is the swiftest in its movements of all the planets. With the exception of some of the satellites, it has an orbit that departs most from the circular form. In other words, an orbit marked not only by the greatest eccentricity, but also by the greatest inclination of all planetary orbits to the ecliptic. This eccentricity of the orbit is such that the Sun is 7½ million miles out of its center, while the actual distance of the planet from the Sun ranges from about 29 million miles to 53 million, or a mean distance of about 36 million of miles. The velocity varies from 35 miles a second when the planet is at perihelion, or nearest the Sun, at the pointed end of its oval course, to about 33 miles a second at aphelion. To explain the perturbations in Mercury's motion, Abbe Moreau has recently advanced the following hypothesis. The Sun is unquestionably surrounded by matter which gives rise to the observed phenomena of the corona. Photographs made during the eclipse of 1905 showed an outer corona extending to a hitherto unsuspected distance from the Sun. This outer corona is ellipsoidal, and its major axis is very nearly coincident with that of the zodiacal light. This region, then, is filled with a resisting medium, composed of matter which is gradually falling in toward the Sun. The mechanism of this fall, or contraction, is very complex, and as we have no idea of the identity of the matter, it is difficult to calculate its changes in form. The resistance which the medium opposes to a moving body is likewise difficult to estimate, but we know from the observed acceleration of comets that this resistance is by no means negligible. At the epochs of maximum coronal development, this resisting medium may easily extend to the orbit of Mercury. Hence, that planet, in its revolution around the Sun, must traverse masses of rarefied gas and swarms of minute particles by which its course is modified. We are far from knowing the quantitative effect of the resisting medium, and much study of the corona will be required to complete the solution of this interesting problem. Because of the lack of surface markings, the rotation periods are very uncertain. Recently, Professor Macquargue in France has deduced a rotation of 24 hours 8 minutes. G. Schiaparelli has put forward the view that both Venus and Mercury rotate in a time equal to the individual period of revolution around the Sun, and thus always turn the same face toward the Sun. Such a motion, which is analogous to that of the Moon around the Earth, could be easily explained as the result of tidal action at some past time when the planets were, to a great extent, fluid. This may be true, as Mercury is one of the planets which has no moon, and consequently will be influenced directly and solely by the Sun insofar as tidal phenomena are concerned. These tidal effects must be especially severe on account of the proximity of Mercury to the Sun. Because of this lack of a satellite, the mass of the planet is very difficult to determine. At various times Laplace, Encke, and Leverrier have given values of 1/9 to 1/30 of the Earth's mass. The first convenient opportunity of placing this planet in a gravitational balance of determining its mass was presented in August 1835, when Encke's comet, in the course of its eccentric path through the solar system, penetrated within the orbit of Mercury at its perihelion. The attractive power of the planet produced only a slight deviation from the regular course of the comet, sufficient, however, to show that the value previously assumed for Mercury's mass was nearly twice too large. At the same time, the calculations made from these data have not removed the uncertainty that still prevails upon this point. Simon Newcomb decided on a value of about 1/21 that of the Earth, while William Harkness made it 1/25. Beyond its motion, comparatively little is known of Mercury. The spectroscope seems to indicate that the atmosphere of Mercury contains water vapor, just as does the Earth, but the studies of Professor Lowell at Flagstaff, Arizona, do not show any signs of clouds or obscurations, and there are no indications of any atmospheric envelope. In fact, the surface of Mercury has been termed colorless, a geography in black and white. The first student of the surface of Mercury was Johann Hieronymus Schröter (1745 1816), who, as will be seen, was a pioneer in the study of the topography of the Moon. In April, 1792, Schröter concluded from the gradual degradation of light on its brightly illuminated disk that Mercury possessed a tolerably dense atmosphere. During the transit of May 7, 1799, he was struck with the appearance of a ring of softened luminosity circling the planet to a height of 3 minutes and about a quarter of its own diameter. Referring to this ring as softened luminosity, Agnes Clerk writes in her History of Astronomy: "Although a mere thought in texture, it remained persistently visible both with the 7-foot and 13-foot reflectors, armed with powers up to 288. A similar appendage had been noticed by Desplantades of Montpellier, November 11, 1736, and again in 1786 and 1789 by Prosperin and Lagergus. But Herschel, on November 9, 1802, saw the preceding limb of the planet projected on the Sun cut the luminous solar clouds with the most perfect sharpness. The presence, however, of a halo was unmistakable in 1832, when Professor Moll of Utrecht described it as a nebulous ring of a darker tinge approaching to a violet color. Again, to Sir William Huggins and Stone, on November 5, 1868, it showed as lucid and most distinct. No change in the color of the glasses used or the powers applied could get rid of it, and it lasted throughout the transit. It was next seen by Christie and Duncan at Greenwich, May 6, 1878, and with much precision of detail by Trouvelot at Cambridge, Massachusetts. Professor Holden, on the other hand, noted at Hastings on Hudson the total absence of all anomalous appearances, nor could any vestige of them be seen by Bernard at Lick on November 10, 1894. Various effects of irradiation and diffraction were, however, observed by Lowell and W. H. Pickering at Flagstaff, and Davidson was favored at San Francisco with a glimpse of the historic aureola, as well as of a central whitish spot which often accompanies it. That both are somehow of optical production can scarcely be doubted. The planet's physical condition presents many problems, and the spectroscope affords little information as to its constitution. As it shines only by reflected light from the Sun, its spectrum is but a fine echo of the Fraunhofer lines. An atmosphere like that of the Earth was suspected, however, by H. C. Vogel in 1871 from his spectroscopic studies, tho on the very slightest grounds. Later observations made at the Potsdam Observatory by Miller confirm this conclusion and demonstrate that Mercury has a rough rind of dusky rock, which absorbs all but 17% of the direct light radiated upon it by the nearby Sun. This would seem to show the utter absence of any appreciable Mercurian atmosphere. The probable lack of atmosphere is also shown by the circumstance that when Mercury is just about to transit the face of the Sun, no ring of diffused light is seen to encircle its disk, as would be the case if it possessed an atmosphere. According to the Belgian astronomer Stroobant, the linear diameter of Mercury expressed as a fraction of the Earth's is 0.350 instead of the previously accepted 0.373. The radius 2,232 kilometers, 1,386.7 miles, and the volume compared with that of Earth is 0.042. End of section 15.